Good morning, good afternoon, good evening, whenever and wherever you are. My name is Anna Rochelle, and today we are in Algebra 2, Chapter 6, Day 1. We are going to talk about exponential growth and decay, the graphs, and the word problems. So we're really doing just a couple of things specifically for graphs and specifically for word problems. We are going to take a look at some formulas that we're going to need in order to help us solve these word problems. But this particular section is mostly word problems anyway, so really that's what we're looking for. So let's go ahead and let's get started. So an exponential growth or an exponential decay function is really, well, what's happening is we are looking at y equals some sort of number to the x power. Okay, that's what, in its most basic form, this is the parent function. Sometimes you'll have a number that multiplies to this. Sometimes you'll have transformations of the graph moving left, right, up, down. But typically, this is the basis. So what does that mean in terms of the graph? So let's say I replaced b with 3, for example, to the x power. So we're going to go ahead, we're going to make an XY table, and we are going to choose -2. That's way too close. -1, 0, 1, and 2. And we are going to solve for y by replacing this x. So really, I'm going to have 3 to the -2nd, which is 1/9. I'm going to have 3 to the -1st, which is 1/3. Also, nobody really likes graphing 1/9, but we're going to do it anyway. We are going to have 3 to the 0th, which is 1, 3 to the 1st, which is easy 3, and 3 to the 2nd, which is 9. So when I graph this exponential function, and it's called an exponential function because you have x as your exponent, right? Your unknown is the exponent. So the exponent is always constantly changing. We are going to graph these points. So yikes, this is not a very straight line, but that's fine. We will get the point across anyway. Okay, so this is the easiest point to graph, and I know how to graph these points is because I take the x and the y, and that's one of my points, okay? I take the x and the y, and that's one of my points. Again, I take the x and the y, and that's one of my points. So these three are somewhat easy. This, guys, is like, not so fun. This guy, oh, even more not so fun because you're looking at -2 and 1/9 of that box, right? So while my graph looks very clean, your graphs probably have lines going like this. Yikes, especially if you're using graph paper. And they're probably evenly spaced, if I'm not mistaken, correct? Yes. So when you're looking for 1/3 on the y-axis, you're looking at like a very interesting place, right? You're taking that whole space in your y and you're dividing it into 3, and you want just 1/3 from the bottom. Anyway, that looks like not fun. So that's not the first thing I'm going to graph, okay? And also, I'm going to get rid of these. So I'm going to say this is 1, 2, 3, 4, 5, 6, kind of like that. Oh, but I need 9. So actually, here's what I'm gonna do. I'm gonna move this down here. We're gonna do that. Okay. So then I'll cut in half, in half, in half, in half, half, and half, and half. So that gives me 1, 2, 3, 4, 5, 6, 7, 6, 7, 8, 9. Let's make it a little bit more even. 10. Okay. So 0, 1 is a point. And then I'm going to cut in half, in half, in half. We'll leave that like that. And then in half, in half, in half, we'll leave that like that too. So then I know 1, 3 is a thing. And then I know 2, 9. So I have 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, which is about here. So these are the 3 easy points, and the harder points are like kind of like this is kind of somewhere down here, and this -2, 1/9 is somewhere down here. Essentially, what happens is I have kind of this really crazy increase on the positive side, right? You could say it's almost exponential. Ba-dum-bum. Um, and this very low, slow growth on the left-hand side of the y-axis. Okay. So, because it looks like when we read it from left to right, we are increasing, we are going up, right? This is called an exponential growth function. Okay. So first, we know this is a growth function. Second, we can tell that this function has a 0, 1 point. And I'm going to say it doesn't really matter what this number is because we know anything to the 0 power is always going to be 1. So that's going to be like your staple point on the graph. Okay. Kind of like when you were doing x squared quadratic functions, you knew that 0, 0 was a thing because 0 squared is 0. Duh, right? Like you know math. You got this. We also know that this point right here, so originally I had y equals b to the x, right? So whatever number is here, this point is always going to be that number. So in this case, it's 1, 3, right? But if I change this 3 to a 7, I'm going to have 7 to the first, which is 7. So it'll be 1, 7, right? So really, this point is actually always going to be 1 comma b, based on whatever this b is, okay? And then obviously it's going to grow, grow, grow exponentially. Now, one thing that we don't see on this graph, and it probably would look a lot better on Desmos. Here's a plug for Desmos, I guess. This particular side of the graph is going to continue to get smaller and smaller and smaller and smaller and smaller. But it will never be 0 and it will never be negative. Now, it'll be super small that you'll think it's 0, but it will never cross that x-axis, okay? Because you're always going to take 1 over whatever this is going to be, right? Because 3 to the negative second is the same thing as 1 over 3 to the second. So I could have 3 to the negative 22nd, well, 1 over 3 to the 22nd, which is going to be a ridiculous number, right? 3 to the 22nd. But if you do 1 divided by that, it's going to be a ridiculously small number. So it'll get smaller and smaller and smaller, but it'll never hit 0 because you're always like cutting half, cutting half, cutting half, cutting half, right? So that's kind of where we are. Okay, so this is a growth function. What does it mean to have a decay function? So a decay function is still going to be exponential decay, still going to look like this. But in this case, I think a decay will either be b to the negative x or 1 over b to the x, which is actually the same thing because when you have a negative exponent, you want to make it positive, right? And you want to go in and you want to take this and put it into the denominator if it's in the numerator, which is exactly what we're doing here. So let's, for example, say I have 4 to the negative x power. That's the same thing as 1/4 to the x power. Okay. So we're going to create an XY table. Ooh, that was a terrible line. Let's do it like this. Okay, well, whatever, it's fine. And I'm gonna actually start from 3, -3, -2, -1, 0, 1, 2. And we are going to replace the x with all of these numbers. So I'm gonna have 4, or actually let's do 1/4. I like 1/4 better. To the negative third power. Anytime I have the negative power, I need to make a reciprocal. So really, this is 4 to the third power, right? Because I'm going to make this a positive and flip this. 4 to the third power is 64. We are not graphing that. Thank you very much. But I did need you to see that. Okay. Then I have 1/4 to the negative second power, which is the same thing as 4 to the second, 16. We probably also will not be graphing that. exactly. Then I have 1/4 to the negative first power. That's going to be 4 to the first power. That's 4. We will for sure graph that. Remember that we said that anything to the 0 power is 1, so I'm not even going to bother. Then I have 1/4 to the first power is just going to stay 1/4. And then 1/4 to the second power, that means I'm going to have 1 to the second over 4 to the second, which is the same thing as 1 over 16. Now, I would like to bring your attention to this. I have 4 down here and 4 up here. I have 16 down here and I have 16 up here. Those numbers are going to flip-flop. So for example, I'm going to go all the way to the front. If you'll notice, I have 3 here and 3 in the denominator, 9 here and 9 in the denominator. Those will flip-flop, assuming there's no transformations, okay? So if there are no transformations, those will all be the same, okay? Let's go back to this original problem. So now let's go ahead and let's graph this. Let's make some changes. Okay. All right. Whatever. We'll figure it out. So I'm not graphing this, but if I did want to, it would be negative 364. It would be like, if I were to break this up, negative 364 would be like somewhere up there in infinity. I don't even know. Okay. I mean, I do know, I just not in this scale. It's a little bit funky. Okay. Negative 216 would probably be like somewhere here. Negative 1/4. Now that's a little bit more realistic. So if we divide 16 into fours, this would be like half. This would be 8. 4 would be somewhere here. 0, 1. Remember that 0, 1 that I said was going to show up all the time? So here we go. Actually, that's more like 2. 0, 1 would be down here. And then I have 1 1/4, which is so gross, right? Because, it is what it is. And then 2 1/16, which is even more gross because it's like way down. Anyway, so this is kind of like going down really quickly and then going down slowly. Okay. So this is my decay graph. This is I don't know why my C looks like another E. This is my exponential decay graph. Um, Actually, if I really wanted to, I could extend it here, and then you'll see that it really does go down very quickly. Again, I would strongly recommend putting this into Desmos and calling it like really good. Okay, so that's one thing that we know we have in common. We have this 0, 1 point, this 1b point, right? And then we also have the asymptote that shows up. So an asymptote is something, it's essentially a line that kind of is imaginary almost. Doesn't really show up. I'm going to change it into a different color. In this case, my asymptote here is y equals 0. That's where my graph kind of goes, and goes super close, but never really crosses, okay? Because it never really crosses, it's considered an asymptote. It's considered approaching infinitely. Okay. Let's talk about interest. So we're going to like switch gears for a hot second and then we'll go into the word problems. So if you need a break, go ahead, take a break and then come back. Okay. Now that you're back or that you've never left, in the past, interest in middle school was very simple. Okay. So in fact, you had it called simple interest. Simple interest is I equals the principal times the rate times the time. This does not exist in real life unless it's between two friends. Hey, after 10 years, you're going to pay me back my $50 with 10% interest. You're going to end up making $5, whatever. Okay. This does not show up ever again. Later on, you have something called an annuity. That is when you take your principal and you multiply your principal plus plus the rate. Um, the reason why you're doing one plus the rate is because you're doing 100% of the principal time plus the rate. So you're taking like 102% of the principal, which then comes back to you in this annuity. So what does that mean? At this point in Algebra 2, probably you've learned about the Great War, World War I, World War II in history class. You'll remember that during that time period in history, America was selling something called a war bond. Now, war bonds are essentially the government was selling you a piece of paper and they would make a promise to you saying that they're going to return your $250 or 500 or however much money it was, I don't remember, with some interest over time because the government needed your money so that they can get supplies, food, I don't know, guns, whatever it is they needed. Okay. It was beneficial for the people. Here's my $250. I don't need it right now. There's a war going on. What, I'm going on vacation? No, right? And it was beneficial for the government because the government had money. It was beneficial for the person as well because the person was able to get some money back at the end of the time period that the bond was valid for, or something along those lines. And in this case, we're going to multiply it by, sorry, not multiply it, put it to the t power, which is however long the time is, right? So we still have the same essential things, they just show up a little bit differently. Okay. This is called interest in the real world. Okay. This is how you find out how much money you're going to make on a certain bond or a certain whatever over a period of time. There's also something called compound interest. It uses the same idea, the annuity, right, is equal to the principal of 100% of the principal plus, excuse me, the rate over how often it is compounded. Okay, and I'll tell you what compounded means, and then we take it to the compounded amount of t time. So when something is compounded, that's kind of more realistic, right? Let's say I put $100 into my bank account, my savings account, and my savings account is going to grow at 1%. So first year, I'm just going to have, first month, I'm going to have $100, right? January 1st, I put in $100. February 1st, I now have the original $100 plus that 1%, which is $1. So I have $101 at the end of February 1st. March 1st, what's going to happen is I haven't touched anything in my account in February. So March 1st, I'm going to have $101 plus that 1% that I earned on $101. 1% on $101 is $1.01. So really at the end of March 1st, I'm going to have $102.01. Some people say it's the beginning of March 1st, some people say it's the end of March 1st, whatever. So then I'm going to go April 1st. I'm not touching my bank account at all. So I'm going to start off with this $102.01, and I'm going to add 1% on that. That actually ends up being something like $2.02. No, that does not make any sense. $1 and 102. Okay, so then I end up with 104.01. This does not seem right. Okay, we can check out the math a little bit later. I think that's fine. But essentially, the idea is this really doesn't seem right. I'm going to check this and be back. So I checked, and this is really interesting. When you do this times 0.01%, you get $1.02, right? Because you just move the decimal over, blah, blah, blah. So when you add this amount, you end up with, I just did the math wrong. Yikes. Okay. That's really sad. Okay. That's why it looked weird. It should be 103.03. Okay. Anyway, so none of this is important because you're not doing this math. This is too much math. Not none of it. I need you to understand that it's compounded. Compounded means at whatever point in time, you are taking that amount that's in your account and you're adding the 1% on top of it. You're adding it again and again and again on whatever's in the account. Okay. So you can actually compound things monthly, and your N would equal 12 because there's 12 months in a year. You can compound your interest quarterly. So based on whatever's in the account on at that quarter date. So that's going to be quarters, it's 4 quarters. You can compound it semi-annually. That's going to be N is 2. Bi-monthly will be 24. Like daily will be 365. So that kind of just really depends. And that number is going to show up twice in your formula. Okay. This is called compounded interest. So now compounded interest or compound interest. I think it's compound, not compounded. Okay. So let's get to the things that really matter. Word problems. There's a few things that you can be asked to do in word problems. First is write a function. Okay, that's fine. We know that something is depreciating. Depreciating means it's going down. So this is going to be a decay. We know that the rate is 14.3%. And we know the initial principal or the amount, right, is going to be 6,500. So I'm going to go into my medium interest, not my simple, not my compounded, because it doesn't say that something is compounded here, right? I'm going to go one, actually, I'm going to go one minus because depreciates means minus. So this is the original formula that I need to replace information for. I don't know my final, but I do know my principal is 6,500. I know I'm going to subtract 0.14143, and it's going to be to the t power. I can leave this like that as is, no problem. This is totally acceptable for part A. Part B says find the value. So the value is what we're looking for after 3 years. And the time is what we're given. The time is 3 years. That means I'm going to replace that t. This is totally acceptable at this point in the game. When you are asked to, I'm going to do this math real here on the calculator, off to the side. So this is going to be 0.857 to the third power. Let's take that to the third. And that's going to be, yikes, a crazy number. It should be 0.629, da 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 da. And then we are going to multiply that by 6,500. And we are going to get our annuity, or about 25, 4,091.25. So at the end of the 3 years, my computer is worth $4,091. Honestly, with technology, I don't think that your computer is going to be worth that much. I think it'll probably be less with technology increasing as we go. Also, I don't know who's buying a 6.5 grand computer. Maybe I'm just buying the wrong computers. Okay. Those are acceptable. Okay. Here it says I write a function, And then we want to know what's going to happen in year 10. Again, also totally acceptable. So let's go ahead. We understand that a population is increasing, so it's going up, so it's going to be a growth. So I'm going to have 1 plus the rate to the time power times the principal is my annuity. They use the A and the P very, very loosely. It doesn't always mean principal and it doesn't always mean annuity. In the case of these bears, the bear population growing, there's no money being exchanged, right? Like this is not a money situation. So there's no annuities and there's no principal. It's just the beginning amount and the ending amount. Okay. We know that the rate is 2% per year, and we know that there's 1573 bears this year. So I know my function is going to be A equals, or you could do Y equals 1 plus 0.02 to the t power. This is my function. Then you're being asked what's going to happen in year 10. So I'm going to take 1573 times 1.02 to the 10th power. And I'm going to solve that. Now, in some cases, in some calculator cases, you could actually take this whole bit and plop it right into your calculator. In other cases, like if you're using an iPhone calculator, it's not going to be quite as easy. You're going to have to do this 1.02 to the 10th power first. So I'm going to do that off screen, 1.02. It should be an x to the y power or y to the x power. You're going to go to the 10th power. And you should get about 1.21899, blah, 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 right? And then that number we're going to multiply by 1573. So times 1573 to get our final bear population or our ending amount is going to be about this many bears. Because it's 0.4, I'm going to leave it as 1917 instead of rounding it up to 1918. And that's how many bears we're going to have in 10 years. So it's really all about finding the information that you need, pulling it out of the word problem, plopping it into that word problem, and then going from there. Okay. For a period of time, an island's population grows at a rate proportional to its population. I don't know that that's super important, but okay. Growth rate, so we know growth and we know the rate. That means I know I'm going to have 1 plus r to the t, and I know I'm going to have a population, and I know I'm going to have an ending population. The current population, they're telling me, is 1543. And then they want to know what's the population going to be like in 5 years. So we're going to go ahead and we're going to write out a formula. So A equals the current population times 1 plus 0.038, which is the rate, the growth, to the t power. Now we're going to replace. So this is my formula. I'm going to go A equals 1542 times this business to the fifth. So I'm going to go off screen. It's going to be 1542. Sorry, not 1542. 1.038. Again, y to the x or x to the y power of 5. You're going to get about 1.2. And then we're going to multiply that by 1542. And we're going to get a final answer of about 1858. So in about 5 years, with this population growth, there should be 1858 people. Okay, and that concludes, I believe, yep, that concludes our Algebra 1, Algebra 2, core, Chapter 3, Day 1 lesson. I look forward to seeing you in another video. Bye.